could cause me issues. Messaged about it. We were told when the deadlines were, guys, you can't just complain. Remarkably, on extensions to deadlines.
Okay, so yesterday we talked about the fact that a random effects model, meta-analysis model, can allow for heterogeneity, but what we'd like to do is explain, or see if we can explain that heterogeneity. I'll talk about meta-regression model. I'll show an example in the next set of slides. Final thing I just wanted to talk about before we move on to those is publication bias. I think I sort of said what this was before. So this is when we're doing a meta-analysis or systematic review of meta-analysis, we're reliant on the studies that we find. And typically these are published in journals and so on. And publication bias is the concern over publication bias is that positive results, so results showing a treatment effect or a risk factor, that are statistically significant, are more likely to be published than ones that aren't. And if that is the case, then our analysis is biased. Okay, and there are various potential explanations. And I talked about these before. About it could be investigators not submitting, prioritising writing up positive results over negative results. It could be reviewers. So when you send a paper to a journal, it gets sent out to peer reviewers, other people working in the field, and they might again be more positive towards studies which are showing positive results. Journal editors, again, they want people to read their journal, so they're looking for, interesting results and so on. Or it could be, research funding bodies. So there's some people might argue that pharmaceutical companies, which obviously fund a lot of pharmaceutical research, again might be more likely to want studies published and some that are positive, that show their drug in a good light. So that's the idea. Obviously, if there is publication bias, it can cause problems. But the first thing really is to try and assess whether or not there is. And one way of assessing publication bias is to do what's called a funnel plot. We'll look at a couple of examples in a minute. And this is basically a plot of, on the x-axis is the outcome measure, so log odds ratio perhaps, or difference, mean difference, whatever scale you're working on. And on the y-axis is, and there are various slightly different ways of doing it, but is 1 over the standard error for each study. Okay, so if you have a large study, for instance, with a small standard error, you'd expect it to be near the top of the y-axis, higher up the y-axis anyway. And the idea, why this plot is useful, is that if we've done our meta-analysis, we've got our central estimate, our pooled estimate, and if there isn't publication bias, you would expect studies to be randomly distributed about that overall effect. Okay, so let's have a look at some examples. So the plot on the left is what we might expect to see. So we can see that the overall central estimate is somewhere around, I should have put it on actually, is here. And we're getting random scatter, reasonably random scatter about that central estimate. And the reason it's called a funnel plot is that you would expect, essentially we're assuming a normal distribution. So you would expect some large studies to be up here, smaller studies more spread out. Okay, so basically you're looking for something like a normal distribution. The plot on the right-hand side, though, we seem to be missing this right-hand tail of the distribution. And essentially that's what we might say that there seems to be something going on. It seems that we're missing some studies here, and if they were there, then we'd get a different estimate of effect, a different pooled estimate. And that's essentially, so the most useful thing really is just to do a funnel plot and have a look at it and see whether or not you think you're missing some studies. Now, and here we can this plot hasn't come out very well. This is the aspirin example we've been looking at, and you know, when you've got so the top plots are quite easy to you know, assess subjectively because there's lots of studies. It gets a little bit harder when you know, with the aspirin example, there are only 7 studies. So, you know, most of them are over here. We do seem to be missing this tail, left-hand tail here. So, you know, we might conclude that there's some evidence that there's publication bias. So as I said, you can look at the funnel plots. Another way is there is a test I should have put on here. It's called an EGGER test, E-G-G-E-R, which essentially is a meta-regression of effect size versus standard error. And you would basically expect the slope to be 0 if there wasn't publication bias. Okay, so you can do a test, but you know, actually looking at a funnel plot is probably, you know, certainly the first thing that you should do. Clearly, you might still say, well, if there is publication bias, what do we do? Really, the first thing is to then caveat your meta-analysis results with sort of saying this is what the meta-analysis is showing, but we have looked at publication bias. We think it might be a problem. You know, be wary of our meta-analysis results. People have looked at ways. In fact, a number of years ago, colleagues and I looked at a method called trim and fill, which basically tried to fill in the missing studies. Okay, so tried to predict what the missing studies would have been to make it symmetric, and then recalculated the meta-analysis. Okay. But as I said, for this course, the most important thing is understanding why you might get publication bias, and you know, some simple, you know, doing a simple funnel plot is the first thing to do. Yeah, you could do a meta regression as well. Okay. So the rest of today, I want to talk about some extensions to the methods that we've looked at so far. And in particular, I want to look at Bayesian extensions that allow us to do sort of some things that you know, we can't really do from a frequentist point of view. And I'm going to start off just very quickly going through a Bayesian pairwise meta-analysis, how it differs, and so on. And then look at I suppose three things. We go back and look at meta-regression. You don't really need to do this from a Bayesian perspective, but I'll show you an example. But what is more problematic if you're taking a frequentist approach is what's called adjusting for baseline risk. I'll explain what that is. And extending our pairwise meta-analysis refers to the fact that we've got 2 treatments or 2 exposures or two of something, and we've got a number of studies and we want to pool them. In practice, there are often a number of studies in looking at the question that you're interested in, and they may have compared different treatments. And what we want to do is to try and put all that evidence together in what's called a network meta-analysis. It's also called a mixed treatment comparison. And again, taking a Bayesian approach really helps with that. So we'll look at our aspirin example again. Our fixed effects model, we sort of said that we're assuming that the log odds ratios come from normal distribution with some common mean D. Okay, so this is exactly as before. But if we want to take a Bayesian approach to fitting this model, as I said, it doesn't really give us many advantages here, but just to illustrate the idea, if we're taking a Bayesian approach, we would have to put a prior distribution on any model parameters. I am sort of assuming people are familiar with Bayesian. Yeah, everyone. The idea, anyway. People nodding. So we'd have to put a prior distribution on D. So that's the only model parameter. We've got the Y's are the observed log odds ratios, and the V's are the variances that we've calculated. So the only parameter is D, or in the other notation, theta, whichever you prefer. And we could put a vague prior distribution on D. So D is the pooled log odds ratio. So it can take values anywhere on the real line, from minus infinity to plus infinity. So we might put a normal prior on D, because it can take positive and negative values, centered at 0, but with a very, very large variance. So basically, we're sort of saying we don't know anything about D. We're being uninformative. Now, in these notes, I talk about a package called Winbugs. This isn't examinable. It's don't worry about there's some slides with code on. I'm not going to go through those. What I will say is that these sorts of models that we're going to look at, we estimate the parameters. Clearly, this is a very simple model. We've only got one parameter. It's actually a conjugate model. So normal prior, normal likelihood, you'll get a normal posterior distribution. So you could write down the posterior distribution. But obviously, as we look at more complex models, you can't. And so what we do is we use, one approach is to use Markov chain Monte Carlo, which, again, people may have heard of, even if they don't know the idea. And I've gone and taken a slide out which explained it, actually, which is a mistake. So when we've got many parameters, we can't get analytic solutions to our Bayesian models. And so what we have to do is we have to use MCMC techniques to get samples from the posterior distribution. That's probably as much as you need to know. That basically, we're simulating from the posterior distribution, and we're then using those draws to get our marginal posterior distributions for parameters like D. Okay, so that's probably as much. And there are various packages for doing this. Winbugs is one. JAGS is another that was developed by Martin Plummer in our department. So I tend to use JAGS for these sorts of things. Okay, so let's go back to our example. I'll skip over some of the slides. We've calculated our log odds ratios and variances. We've seen that before. This was the table we had before on the data. So the Y's and the V's and obviously the weights. Okay, we've seen that. Okay, I'll skip over this code. So we've run our MCMC model. when you're running MCMC, there are questions over how long do you run. Well, there are questions over you have to give it starting values, and there are questions over how long you run it for. Okay, I'm going to gloss over those sorts of issues. We've run our model. We've actually run it for, I burnt it in for 5,000 simulations, so basically threw those away and collected the next 10,000. Okay. And here we've got, you might sort of say that the graphics aren't very good. Yeah, this is the high quality graphics you get out of packages like Winbugs. These are the posterior distributions for D, the log odds ratio, or we've transformed it onto the odds ratio scale. Okay. And those 10,000 samples, the mean was 1.116 for the odds ratio, and it's got that standard, really that's a standard error, and it gives us a 95% credible interval, because we're being taking a Bayesian approach. This is now a credible interval, not a confidence interval. So we can see that, if you remember from yesterday's lecture, or time before, if you did a frequentist analysis, you'd get an odds ratio of 1.11 with that confidence interval. And here we've got something very, very similar. Okay. And you'd expect that, because we've put a non-informative prior distribution on D, our only parameter. So really the data, our 7 studies are dominating, and we get very similar answers. So, yeah.
Just when we do these MCMC samples, it's not just here, but several sources. It seems that we gravitate towards the median as opposed to the mean. Why is that?
Yeah. So why would you use the median rather than mean? Typically, in this case, they're not that bad actually. If you have a skew distribution, then you typically report the median because it's skewed. Okay. So that's the main reason why you might do. Here, you can see that actually it doesn't really make much difference whether you report the mean or the median. Because the both posterior distributions for the log odds ratio and for the odds ratio are fairly symmetric. So you wouldn't expect. Now the reason, sometimes though, you find that when you transform onto the odds ratio scale, the distribution, you might get something that's fairly symmetric on the log odds, but a bit skew on the odds ratio. And so I would tend to report the median.
I guess the flip of that question then is, why would we ever report the mean?
Okay, there are some situations where you would. So for instance, if, and a lot of my work's in health technology assessment, where we're interested in combining this clinical effectiveness with perhaps cost effectiveness results, and you'd want the mean effect and mean cost in that situation. Yeah. So it's a good question though. I would tend, if it's skew, I would tend to report the median. Otherwise, the mean. If it's not skew, they're going to be similar anyway. So, okay. So that was just our fixed effects model. So there's no real benefit from doing a Bayesian analysis, and we get the same answers with a non-informative prior. So let's look at a random effects model. So this is the model that we talked about yesterday. In terms of parameters, we've now got 2 parameters, unknown parameters in the model. We've got D, the pooled mean, and tau squared, the between study variance. Okay. So we need to put priors on both D and tau squared. And we're going to put the same prior on D. not very, very vague normal distribution. Now, tau squared is more problematic, and this is true. It talks about Wimbergs, but this is true generally. Tau squared is a variance, so it can't go negative. So we can't put a vague normal prior on tau squared, because obviously if we put a vague normal prior on, it would allow negative values of tau squared. And what would happen is basically the model would blow up, because the prior is sort of saying negative values are okay, but actually the model is sort of saying tau squared is always positive, so you get a prior, what's called a prior data or prior model conflict. So we have to think about different prior distributions, and there are a variety of ones that people have looked at, and here I've sort of said you could put, so tau is the between study standard deviation, you could put perhaps a uniform prior, so 0 to 10, or some upper limit. 10 is very large actually, some upper limit to the uniform. So what that's saying, one tiny bit of chalk, what that's saying is that. So any value between, let's say 2 rather than 10, any value of tau between 0 and 2 is equally likely. You know, not an unreasonable thing to assume. What else could we do? Well, another prior that people often have used in the past is what's called an inverse gamma prior on tau squared or tau. And that looks something like that. So it should be a bit closer to the x-axis. It gives very, very high values to, high density to low values, and much lower density to bigger values of tau. So that's another one. Now, the reason people use that one is that it approximates, people may have, in a Bayesian course, you may have seen priors like that, 1 over the variance. So if you've got a normal distribution and unknown variance, you could put this 1 over sigma squared prior on sigma, and that's what's called a Jeffreys prior. And the reason why that's attractive is that it's invariant to transformations. So even if you transformed sigma squared, the effect of the prior would be the same. So people basically use this inverse gamma distribution to approximate this 1 over sigma squared. Another prior, just to mention it, another prior, which actually is quite a nice one, is what's called a half normal. So basically, imagine a normal distribution centered at 0, and we're taking the upper half of it. Okay. And the reason that's quite nice is, again, you get this decay. The problem with the uniform is that you have to specify this upper limit, and anything between 0 and the upper limit is equally likely, and that's probably not terribly sensible. Right, so let's run our model with this uniform prior. As I said, uses quite a high upper limit, a bit too high really, but anyway. So we've run our model, and we now get, so in terms of the, again, we'll look at the median, 1.148 is our estimate for the odds ratio. And now the 95% credible interval goes from 0.976 up to 1.434. So it's a lot bigger, well, it's bigger than for our fixed effects analysis. And this is what I was saying yesterday, that when we fit our model classically, we basically get an estimate for tau squared that we then plug in. Okay, so it's a plug-in approach. We estimate tau squared, plug it in, take the sort of estimated value, plug it in, and then estimate D. Now, when we're fitting this in a Bayesian framework, we're not doing that. We're estimating the parameters simultaneously, and the uncertainty in tau is taken into account in the analysis. So you will always, I said this yesterday, you'll always get slightly wider, for a random effects model, you'll always get a slightly wider interval in your Bayesian analysis than you would in your frequentist, because it's done it properly. It's taken that into account. Now there are ways of doing it properly in a frequentist approach using what's called profile likelihood methods, but no one uses them. I think I looked a while ago, and there's about 2 papers that have used profile likelihood. And the reason is because it's computationally a bit more demanding, and so all the packages that do meta-analysis and so on take this plug-in approach because it's easier to do. Okay, and they're all underestimating slightly the uncertainty because they've not taken it into account. Okay, so we're now starting to see why actually using a Bayesian approach is starting to give us something a bit different, a bit more than frequentist, and I won't go through the plot. Now, obviously, as in any Bayesian analysis, and particularly for meta-analysis, where we're putting these we're trying to put these non-informative priors on a variance, and we might not have many studies. So here we've only got 7 studies, so we're effectively estimating that tau squared parameter on 7 data points. So that's not much. And what we would be concerned about is that the prior that we put on the variance parameter might be having an effect. It might be not quite as vague as we would want. And so it's really important to do a sensitivity analysis. And so here we've run the model with 3 different priors on 2 of them on the standard deviation scale. Precision here is 1 over the variance. So we put, or you can either put a gamma on 1 over the variance, or you can put an inverse gamma on the variance. The same thing. So we've looked at 3 different priors and plotted the odds ratio assuming the different priors. Okay, and you can see that broadly you're getting very similar answers, both in terms of point estimate, just about to the point estimate, and the credible interval. The gamma one is slightly narrower. Okay, and the reason it's slightly narrower is, remember, it's putting a lot of weight, a lot of density on very low values. Okay, and if tau is very small, then that will reduce your uncertainty in the odds ratio. So the key thing to take away is that, and it's particularly true of meta-analysis because we often don't have many studies, that if you're doing a Bayesian analysis, you need to look at sensitivity to prior distributions. Now, I haven't done actually, a sensitivity to the prior on D, so that very vague normal. And to be honest, that's going to have very little impact. but this prior on the variance or some function of the variance could be quite important. So it's always, you always need to do a sensitivity analysis. Yeah.
Like, I don't know quite how to structure this question, but like in Bayesian psychology, over in the psychology department, they made the point of you don't change the distribution, but you actually change just the parameters for your sensitivity analysis. Is that?
No, not sure. I'm not sure I'd agree with that. Here, okay. I said 10 was quite large, and I'll show why it's large in a minute. What I would add to this slide is prior 4, which is uniform 0, 2, say, something like that, to see whether or not changing that upper limit changes the results. But no, I think it's really important that you look at other distributions potentially. I mean, they've got to be sensible distributions, but which all these are, that all of those are, between 0, only on the positive real line. So, yeah, interesting point. I won't make comments about psychology. Okay, so, right, let's think about tau and what it means. So tau is the between study heterogeneity. And we could think, if we've got a value of tau, maybe we've estimated it, or maybe it's part of the prior or whatever, we could look at what that means in terms of the study estimates themselves. And so, essentially, if we calculate d plus or minus 1.96 times tau, that will mean that 95% of that theta should be delta. The delta i's will lie in that range. So we can take the upper limit and the lower limit and look to see what we would expect the range of odds ratios to be. So that's one way. The other way is to think about, well, if we just pick two random, again, sorry, that theta should be delta. If we just pick two random studies and look at the difference in their log odds ratios, so delta I minus delta j, say, well, that's going to be a normal distribution centered at 0 with variance 2 times tau squared. And so we can then look at, the absolute difference, which is always going to be positive, so that's a half normal distribution with parameter 2 times tau squared. But the median difference between the maximum and the minimum for any random pair, you can calculate as 1.09 times tau. Okay. So this, that's the idea. Let me show you a table, because this is quite, illustrative. So let's take some values of tau and think about what that means. So you can see that we've got two columns there. One is the range of odds ratios, so basically the maximum to the minimum, and the other is the median ratio for a random pair. So if you just pick two studies, how sort of different could they be? And you can see that, for values of when tau is 1, so this is a standard deviation, when tau is 1, then the max to the min could be 50-fold difference. So the maximum is 50 times the minimum. So huge difference. And if you just pick two random studies, they might differ by 3-fold, basically. So you can see that uniform prior 0 10, the reason I said 10 is far too high, is that, you're really, when you analyse meta-analyses using a random effects model, typically tau will be somewhere between 0 and 2. If it's above 2, then you almost should be thinking, should we even combine these studies because they're so different? So as I said, this table I think is really, really helpful. So yeah, going back to those results, I definitely put a uniform 0-2 prior N as another sensitivity analysis, see whether it makes a difference. I don't think it does in this case, but okay. Okay. I'll just mention this. When we fit Bayesian models, we can use, there are different approaches. One approach to model comparison is using what's called a DIC, Deviance Information Criteria. It's basically a Bayesian AIC or BIC version. We get a measure of fit, the posterior deviance, mean deviance, and a measure of complexity. And so again, we're looking for differences of 3 to 5, to try and choose models. I'll just mention that. Okay. So we could say, well, should we be using a fixed effects or a random effects in this situation? DIC turns out to be negative for these models, for the aspirin example, but really it's the absolute values that are important. So, really fixed effects is probably the better option. Okay. Right. So we talked about meta-regression. So we've done our Bayesian, fixed and random. We could extend those models to meta-regression setting. And this is what we're basically, if you fit a random effects meta-regression model, this is what you're doing, is that now we've got our treatment effect on the y-axis and some covariate age or year of publication or something like that on the y-axis. And we're estimating some overall effect, so beta, how the covariate might affect the log odds ratio or whatever, but that we're still allowing for study-to-study variability. Okay, and I mentioned yesterday that if the covariate is a useful one, you would expect tau squared for this model to be smaller than the standard random effects model. Okay, so that's the idea. We can extend, just in terms of the model, we're basically adding in this beta xi term here. Okay, so as I say, xi is some covariate value for the ith study. So we're just adding it in. Okay, let's have a look at an example. So this was looking at BCG vaccination for preventing TB, okay, so tuberculosis. And the question was, so we've got these 13 trials, they'd randomised people to be vaccinated or not vaccinated, and we've got whether or not they developed TB or not. And the question, so we can do a meta-analysis of that data, that's fine. But the question was whether or not the treatment effect was changed given the latitude of where the study was done, so distance from the equator. So we've got this covariate, which is basically the latitude of where the study was done. So if we fit a random effects model to the data, you can see that there's quite a lot of heterogeneity just from the forest plot. The studies are a bit all over the place, really. Most of them are giving a odds ratio less than 1, so that BCG vaccination is effective. It reduces your risk of developing TB. It's a good thing. Not all of them, though, give that, and some are quite close to 1. In trial 8, very large trial, can't remember how it was, trial 8, 87,000 in each arm, so pretty large. That's absolutely on 1. Okay, you can see that the pooled estimate is showing a beneficial effect, but we've got a lot of heterogeneity. And you can see, and sorry, I can't remember. I think that's probably the standard deviation scale. You know, the between study heterogeneity we're estimating at 0.37. So if you think back to that slide, that's quite, you know, it's quite a lot. So let's look to see whether or not this covariate looks effective, you know, is useful. And so one of the things that we often do is this what's called bubble plot, which is where we plot so on the y-axis we've got the log odds ratio, x-axis our covariate, and each circle is a study, and we basically the size of the study is proportional to the size of the circle is proportional to the size of the study. Okay, so this is this very large study, absolutely, you know, showing no effect. But you can see that, you know, if you had to draw a line on that plot, you'd probably draw a negative relationship. Okay, seems fairly certain that if you fitted some sort of model, you'd get a line showing a negative relationship. So okay, so let's fit a model. So when we're formulating the model, one way of formulating it is to sort of say, well, we've got our two arms, A and B, and we've got the number of, in this case, the number of people who get TB in arm A out of N, R out of N, and similarly for the other arm, okay, with probabilities P, AI and PBI. And we model the logit, so the log of P over 1 minus P in treatment A, so that's the control, is going to be mu I, and the logit for PBI is mu I plus delta I. So okay, let's if you just forget the covariate for a minute. So if this delta I is, well, that's the difference between the logits. So delta I is the log odds ratio. And we want to include the effect of the covariate, so we're adding this beta xi in. So the log odds ratio is, depending on the value of beta, is modified by the covariate value. Obviously, if beta is 0, then the covariate's having no effect. So from a hypothesis point of view, we want to see whether beta's 0, which in this case we don't think it is. Okay, I won't go through the code, as I say, it's not examinable. But let's look at the results. So we've run our model, and we've got, if we look at the posterior mean for beta, it's negative, which is what we thought from just looking at the plot. And if you look at the 95% credible interval, it's wholly negative. So it goes from minus 0.0099 to minus 0.05. Okay. So it looks like there is an effect. If we look at tau squared, again, you could look at the median or the mean. If we just go quick, oh, I haven't got the, sorry, should have run it without, okay. Maybe that's the variance, okay. Sorry, I should have double checked these figures. Tau squared is lower than it was before we added the covariate in. Okay. So it does appear that this latitude is important. And basically we can then also, we can look at the effect for particular, so if we had a study and we knew its location, we could estimate what the effect would be in that location. Okay. And there's a plot of the effect.
There's a decrease in effectiveness, but surely the odds ratio being negative, not negative, but you know what I mean.
So yeah, so if we look at
Good thing because that's preventing the disease.
yeah.
Lower rate of disease.
So did I say relative increase in the odds of developing? If sorry, that's yeah, I've written it in terms of being unvaccinated.
The first line's a decrease in effectiveness. So I thought this would be an increase in effectiveness.
Yeah, sorry. Yeah, it's the second point. So basically, if we're sort of saying, so if we look at this here, that the further you are, yeah, sorry, you're right, that should sort of say increase in effectiveness, that the odds ratio less than 0 is indicating the vaccination reduces your risk of TB. Above 0 increases. And so we get this, our negative slope. Here's the line that we've estimated. So that as you move away from the equator, you're seeing a larger effect. Yeah. So if you were, as I said, if you were, wanted to know what the effect was in a particular location, it seems that it's really important to take the location into account. Okay. Now, one thing that is we can also do is look at what's called baseline risk, because very often we don't have that many covariates in our meta-analysis. Okay, that one we had latitude, but maybe we didn't have anything else. And so one way of getting over that is to use what's called baseline risk. And if basically baseline risk is the effect in the control arm. So the way to think about it is that it's a sort of proxy summary measure of how sick these patients are. So if you had a very high event rate in the control arm, that might suggest that you've got a very sick population. If you had a lower event rate, not so sick. And what we want to do is to see whether or not we could use that as a covariate. Okay, just because of time, I'll skip over. I'll show an example. So this was a meta-analysis of 19 trials that looked at what's called endoscopic sclerotherapy for patients with cirrhosis. And the outcome was the number of patients who bled, so had a hemorrhagic outcome. So here's the meta-analysis. And we can see that sclerotherapy seems to be quite a good thing. So it reduces the pooled odds ratio 0.59. So it reduces your risk of bleeding if you get sclerotherapy by 41%. But again, we can see lots of heterogeneity in the data in our forest plot. So we want to see whether or not baseline risk is important. Now, you could do this. You could, we just looked at our meta-regression model, and you could fit a meta-regression model to the data, with the covariate being the log odds in the control arm. And we get this negative relationship, okay, quite very clearly negative. But there's a problem with that. And the problem is that the odds ratio and the baseline risk are related structurally. So if you had this 2x2 table, the odds ratio calculate as the cross product, baseline risk is part of the odds ratio. So that means if you're fitting a regression model, from other modules, you should know that fitting a regression model where you've got a structural relationship between the two, covariate and outcome, is problematic. But there's another problem. When we calculate the odds ratio, we calculate the uncertainty around it. But there's actually uncertainty around the baseline risk as well. And when you fit that as a covariate, as we did here, you assume that it's known perfectly. Whereas actually there's uncertainty, and that's not taken into account. So we want to be able to fit our baseline risk model. So here, the covariate we're adding is this mu I. So there's uncertainty in it, and it's also related to the log odds ratio as well. Okay. If you adopt, so if you just fit that meta regression model, it could be biased, quite severely biased to the null. But fitting it in a Bayesian framework, actually, you can overcome both of those, because this is a parameter with uncertainty, and you're fitting, the way that you construct the model. It's also, it takes into account the relationship between mu I and delta I. Okay, I'll go there. Does it make a difference? In this case, not particularly. So the black line is what we had before, and the red line is what you would get from your Bayesian model. Bit different, but not radically. In terms of estimates, it doesn't change your conclusion. But basically, it's sort of saying that baseline risk seems to be quite an important covariate. Okay, I'll stop there. Tomorrow's lecture. Tomorrow's lecture, I will talk about the network meta-analysis, and then I'll talk about the repeated measures stuff for ST409 only. I'll send a message out, sort of saying that it will be recorded. So yeah, and I'll also emphasise that this material today, the Winbugs code is non-examinable. Don't worry about that. The rest of it is examinable. The ideas and the models and so on is.
Just a quick question on the word count for the press words. Is there a tolerance on that word count, or is it just max 500 words?
Max
Just
500.
okay.
Yeah, and if you put the word count on it, just so I know.
Essentially, the theme of Bayesian psychology was that everything's a Cauchy parameter, but how wide do you want to make the Cauchy distribution? And this was an absolute headache in the coursework as a result. That you had the combinatoric nightmare of every possible way you could imagine.
I mean, yes, you would change your hyperparameters, the value in the distribution, but like that example, you're fitting very